to merge the different weight changes. Is distributing the images to GPUs at all a hard problem, or?
So, I mean, indeed, that's where the communication bottleneck is, right? Because the images have to be loaded from the network onto CPU and then onto the GPUs. So there are, again, we can binarize and have efficient formats to push the data into the GPUs. But most of the communication cost will come because we have to push the data into the GPUs. And we have to do it continuously. We are not doing it all at once because it's a lot of data. Right? So we cannot send all the million images into the GPU. We can only do it in smaller batches.
So for the problem you've just specified here, how long does what's the runtime look like?
So I'll come to that in a minute. So there is one for sending an image, right? And then there is the other of training. You may have to tune the hyperparameter. So in terms of like training, so again, if you're scaling up, if you take about, I think it was 120 or about 150 GPUs, you can bring it down to a few hours.
And you have to run through the million images many times for the training, is that right?
Right, you may also need to run through it many times. So this is where, like, you have to tune it, right? You have to see what the right hyperparameters are. You have to check on your validation data set how good the accuracy is. So it depends on a lot of factors. That's why it's very hard for us to even tell what the time to run these systems are, because you still have to do the tuning. You have to see whether it's working on your domain, right? So that's why this has a lot of uncertainty. Whether these will work, I mean, they work on ImageNet, whether they work on a different corpus is something that you have to try and tune.
So, and when you say work, I imagine there's some curve of accuracy versus times you iterate through the network.
Right.
So is that just a usual sort of typical asymptote? Is it some kind of sigmoid? What the heck does that look like?
So like it is, I mean, you would like it to be monotonic, right, and increasing, but many times you may just have like very slow growth. Like you're adding more data and then it's not improving. And mostly it's like the wrong choice of hyperparameters to not set the learning rate at the right value. And that's why this is a challenging one. In fact, it's been called a graduate student descent because, yeah, not me, but somebody else coined the term because it's, these are simple algorithms, but on the other hand, to get them to work in practice can take a lot of effort, can take a lot of trial and error, and at the same time, you have to burn a lot of cycles, right? Especially if you're starting from new. If it's many of these image tasks, there's already the pre-trained ImageNet models. You can take them, you can adapt them, you can add a few layers on top of it, right? So it becomes a lot easier. So it depends on how different your data is compared to a model that's already available.
How do you break out of local minima?
So, well, I had in a different talk a trend of like convex and non-convex terms on Google search. And so for a while, convex was the only thing people did, right? And it kept going down and the non-convex was going up in terms of the research papers. And that's the thing, there's been some attempts to explain what's happening with respect to local optimum. One hypothesis is because we are doing stochastic gradient descent, the stochasticity is acting like an implicit regularizer. So meaning it's able to avoid extremely bad local optimum and get to good ones, right? But to me, it's really the choice of hyperparameters. I mean, it's very easy to have these things not work, right? So to get them to work is extremely hard. And somehow these choice of hyperparameters, what you said, like these magic parameters, I mean, it's not thankfully one parameter, but range of parameters makes a difference. But no one knows for sure.
So if you had to characterize, if you view this as a two-dimensional problem, one dimension is the architecture you pick, and the second is the hyperparameters, and you're going for a new corpus, which one do you spend more time on? I mean, which one takes longer to get right?
So that's a good question. The architecture is extremely expensive, right? Because you have to run the entire training process,
right,
and you have to make sure you've tuned all the hyperparameters to get the best performance of that network. and then you add like one more layer or remove a layer. You have to do this over and over again. So most of the time, people choose architectures based on the intuition. If it's images, it's convolution is essential. If it is sequences, you need LSTMs. So there's some standard ones, and they make minor variations. But currently, I mean, architecture search is this meta problem that we would need the next wave of next, in fact, jump in computational abilities to do it at scale.
So convolutional neural nets naturally make it so wherever the object is, you see it. So is there anything that makes it that no matter what size the object is, you see it?
So that's a good point. So there have been attempts to define like group convolution. You can have invariance on any group you can specify. It could be like rotation, could be scaling, but then the operations become very expensive. And so currently, we still don't have a way to do it very efficiently. It's in fact one of the research projects one of my interns is exploring. Can we like use ideas from group convolution but try to approximate it so they can be practical? I mean, ideally would like to do it, but again, it's doing it at this large scale makes it challenging.
I had a question that I think yours was more general, which was the 152-layer model. Is that obviously the best model if you had all the resources available,
Yeah.
or would some applications be better with, say, a 3-layer model?
And in fact, this has already been superseded with something known as DenseNet, which even takes the earlier layers, concatenates, and it's very, very expensive to run, but it has shown better performance. And so there's always this kind of constant arms race. People come up with more complex architectures, and then another group of researchers try to compress or try to make it more efficient and not lose performance. And so as you can see, a lot of it is done through trial and error because we don't have good fundamental frameworks how to think about architecture search.
Has there been any attempt to compare the scale you have here with the brain scale? Is it clearly radically different, or are they getting comparable?
I mean, there has been like ongoing debate between neuroscientists and machine learning people. Some aspects are common, right? The idea of like hierarchy is also part, especially in the visual cortex. There is, although I think it's only 5 or 6 layers. So notion of hierarchy is present, and notion of attention and memory is present. But other than that, I mean, these architectures are way too specific, and I don't see the connection at the architectural level or in terms of the algorithm, right? There is no evidence. In fact, there is evidence that its brain is not doing stochastic gradient descent. So there has been a group of researchers trying to have brain-inspired machine learning algorithms, but they somehow don't work well on on these systems. And to me, like maybe the prior is crucial, like what we are born with, the millions of years of evolution, what it's given us, and we are missing that in these artificial systems.
To your question, Google True North, it's a synaptic computer IBM's building that does this with non-von Neumann computing. Sorry.
No. Well, I guess you can call something synaptic because it's connected, right? Whether it is identical to the brain, probably not. Yeah.
Well, it operates at a much lower power, like 10 watts, 20 watts.
Yeah, so low power is definitely an area we're seeing a lot of growth, and will be, especially with IoT devices, having these small devices, like could be cameras, could be sensors, and where machine learning also happens. That is really important, yeah.
So how do you capture the results of one system and convey that to other researchers who want to either replicate that in some fashion? Because without giving them the data set and the same processor mix that you have to get to that data with results that's embedded weighting, if you will, how do you capture this?
Absolutely. No, that's a great question, and to me, like kind of the last 2 years has been like the Wild West when it comes to machine learning research, because there's been a lot of interest and a lot of people coming into the field. NIPS has grown like 10x every year, right? This growth is not sustainable. And so a byproduct of that has been just so many papers where the model is not available, where the data is not available, it's not reproducible. So there's been a lot of push to have reproducibility in research. So one aspect has been to hold workshops where people make available Jupyter notebooks that you can run the code but also have explanations, and so you can verify how the algorithm is working. And so at AWS we have an extensive initiative along with releasing these deep learning packages to release these Jupyter notebooks that are tutorial based, like you can go there, you can run the code line by line, and at the same time you have explanations of what this code is doing. Right? And this is what I plan to incorporate it into my course at Caltech, where we encourage researchers, we encourage students to not only write their technical paper, but also simultaneously release well-documented code that can be run, release their models, and that's the only way for us to keep up.
So if you take the same code and run it multiple times, it throws random numbers as part of the process. Does it always converge the same way, or might you in one run get lucky and do much better than any other time?
Yeah, so that's why it's always good practice to have error bars, right? So not again all researchers do ideally want well done research to have error bars. They should run it multiple times, see the variability and how they're getting this result. I think the challenge has been the ecosystem because it's grown so fast and it's hard to police. We don't have enough good reviewers as compared to the number of papers that are getting submitted. NIP sold out of tickets within days of opening. This is like the new Burning Man. So maybe you'll find some in black market.